Hey guys, today we're going to talk about series and parallel circuits. The first part of our worksheet is going to deal with just some mathematical practice with the equations that we've gotten so far in this unit. The second part of the worksheet is going to try to give you more of a conceptual understanding for some of these problems, comparing charges flowing through wires with water drops that are going to flow through pipes. First though, let's try to get some mathematical basis to aid in our discussions on the second sheet for when we talk about this water analogy. It would help to have some numbers to use as we compare different situations. So first off, as you look on this worksheet, you're going to see a series of different circuit diagrams with batteries, with resistors labeled as, the battery would be in volts. The resistors would be R1 or R2. The table is what we're trying to fill in, trying to figure out up here what the voltage readings would be across these different circuit elements, the currents and the resistors as well. The subscript T will always stand for the total in the circuit, whereas the subscripts 1 or 2, when we get to later problems, would stand for the individual resistor. So we look at this circuit here in number 1. You're going to have a 12-volt battery. So right off the bat, if you look at our table, we've got a situation where since there's only one battery, well, that would have to be a total of 12 volts then in the circuit, because there's nothing else in your circuit that would add voltage to it. Now, what we learned in our lab, in equations that we've had, is that for a series circuit, the total potential difference, or voltage, would be equal to the potential difference at any individual point in that circuit. So therefore, since there's only one other resistor, this would have to be 12 volts as well. If we look at the resistance, well, there's only one resistor, and we know that value is 10 ohms given in the problem, so let's put that in there. Similarly, from our studies from lab, we learned that for series circuits, the total resistance is equal to any individual to the sum of the individual resistances in the circuit. There's only one of them, and so we don't have to add it to anything. The total would also be 10 ohms. So now we're at least set up to maybe make some calculations. Current, this would have to be read with an ammeter, if you remember from lab, and we don't have one for this worksheet. However, we were able to come up with some equations that relates voltage with current and resistance. And what we decided was that, well, Ohm's law says that delta V is equal to IR. So first I can do that my total is equal to the total current multiplied by the total resistance. In this case, I'm going to wind up with 12 volts is equal to some total current multiplied by 10 ohms. I'm going to wind up with my total current as being 1.2 amps. And I can apply that up here to the problem. Two different ways you can look at to attack this second part. Looking for I1. First off, we talked about in lab that the total current is going to be equal to the current at any individual point. Since charges would be moving at the same rate at any point in this circuit, we can apply 1.2 to that answer. Another way to look at it would be to say that V at the 1 resistor is equal to the current at 1 times the resistance at 1. That would be 12 volts again times the current times 10 ohms again, giving us I1 equals 1.2 amps. So two different reasons for us to wind up here. So a couple things to note, just at the start before we go on to some other ones. Current is 1.2 amps in this resistor, or I'm sorry, in this circuit, and the total resistance is 10 ohms in this circuit. As we look to the next problem, which would be number 2, all we're going to do is just add a second 10 ohm resistor and just see what happens to that overall current that was 1.2 and that overall resistance that was 10 ohms. First off, looking at this circuit, again, there's only one battery, and with it being one battery, it's a 12-volt source. There's nothing else that's adding in voltage to this. So just like before, we're going to make our VT equal to 12. Other things that we know is we have two 10 ohm resistors in here, and so we're going to make R1, well, we know that's 10, and we know R2 is 10 given in the problem. And like before, we said that the total resistance is just the sum of all the individual resistors. In this case, RT would be equal to 10 ohms plus 10 ohms, or our total resistance would wind up as 20 ohms. So what we're showing is that as you add resistors in series, the total resistance goes up because these charges have more resistors and things that are trying to slow down current in that setup. Other things that we know, at least at this point, well, I don't really know the current yet. I don't know the individual voltages yet because there is more places for voltage to be lost. But something I know at this point is the total voltage and total resistance. So like before, we know delta V is equal to IR. Let's apply that to VT equals IT and RT. I know that 12 volts is equal to the total current multiplied by now 20 ohms as my total resistance. And I get a current that is going to be equal to 12 divided by 20, or 0.6 amps. So I can apply that up here. Just like in the first problem, we're saying that the current in a series circuit is equal to the current at any individual part of the circuit. So whereas it was 0.6 before, that would have to be 0.6 amps here and 0.6 amps here. A couple different ways we can get V1 and V2. I think the delta V equals IR example is probably the easiest. So let's just say that V1 equals I1 times R1. We'd wind up saying that V1, which is unknown, is equal to 0.6 amps multiplied by the 10 ohms. We get V1 is equal to 6 volts. We can do V2 equals I2 times R2. Sorry, I'm running out of room here. V2, which is unknown, is then equal to 0.6 amps again, multiplied by 10 ohms, since those were the same values, and you wind up with V2 also as going to be 6 volts. So we can apply that to our table as well. And this should make sense because, again, we said that delta VT is going to be equal to the sum of all of the individual potential differences or voltages. So since the sum is going to be 6 plus 6, well, now it makes sense that that's 12, and you see all of that be applied. So again, let's stop and look at the totals again. Before, we said with one resistor and one battery, we're going to wind up with a total of 1.2 amps and 10 ohms of resistance. Now we're going to add in a second resistor, and you see the overall current has gone down. There are not as many charges moving in the same amount of time as there were before because the overall resistance has gone up. Let's look at a third situation where again we're going to use two 10 ohm resistors, but now in a parallel setting like we talked about in lab. For this, again, just one battery. This shouldn't be anything new. We're going to make that 12 volts right off the start. R1 and R2 are still equal to 10 ohms. That shouldn't be any different. So the same initial setup as before. What's different about a parallel circuit is that the total resistance is an inverse relationship. We're saying that it's equal to the sum of 1 over the individual resistors. So now I've got to look at 1 over this total that I'm trying to find is equal to 1 over 10 ohms plus 1 over 10 ohms. I'll wind up with 1 over RT is going to be equal to 0.2 once you simplify that, and my total resistance does come out to, for this last problem, as 5 ohms for the total. So we paused here in the last problem. Let's do it again. I have two 10 ohm resistors. The overall before was 20, now it's 5. For some reason, as you add in resistors into this circuit, the total resistance goes down. Kind of a confusing thing, and hopefully the water analogy later on will make some sense out of that. Same process before. I've got the total voltage and the total resistance, so let's use our delta V equals IR equation for delta VT equaling IT and RT. I know that VT is 12 volts. I don't know the current yet, and I know that this is now 5 ohms. So IT is going to be 2.4 amps, and I can apply that back up here to the total current. Just like before, I've got kind of 4 missing values. We've got to go a different route than before because we don't have currents as being equal in this case. The charges come around and they actually split up into these two paths, so the total current can't be equal to the individual currents. What is equal, though, is the potential differences, because we learned that delta V, the total, is equal to any of the individual voltages for a parallel setup, different than series. So V1 and V2 are both 12 volts as well. I can use now my delta V at point 1 equals I1 times R1 equation, knowing that this is 12 volts, I1 is what I need, and this is going to be 10 ohms at the side, so I1 will wind up to be 1.2 amps. I can do the same thing down here for delta V2. There's I2 and R2. Again, 12 volts is equal to the current at the second part, and R2 is going to be 10. So I also wind up with I2, equaling 1.2 amps. And let's apply that in here. Now, as you look back here at our equations that we're building, again, these shouldn't be anything new. We talked about these in our lab work. But what we learned about a parallel circuit and currents is that for the total current, that's going to be the sum of the individual currents as you go around that circuit, which now, as you look at the data, 1.2 plus 1.2 equaling 2.4 should make sense for that equation. So let's kind of pause it and look at the totals. As you add resistors in a parallel circuit, the overall resistance goes down and the overall charge flow or current has gone up. So the exact opposite of what we saw up here. Now what I want to show you is just kind of setting you up for this back page. And again, this is your responsibility tonight to try to make some conclusions about this water analogy. But I at least want to show you and remind you what happens with a battery and compare that to the water around pipes to get you started. First off, here's just a picture of this, just so you can see both at the same time, of this first circuit from the worksheet. What we have, and I know we've talked about this to this point, but the longer part is going to be the positive side of the battery. The shorter part's going to be the negative side of the battery. And what we know about circuits is that it's negative charges or electrons that are traveling around that circuit. With this being a negatively charged plate, charges or electrons naturally, without any work from anything, want to get away from that plate. They're repelling. So they're going to come around here, as you see this path, and be attracted to the positive plate. And since these two, at least in this picture, aren't actually touching, it makes sense why they're not going to go back across. So if we were to hit a play button here, and this battery wasn't able to do much into this circuit other than just be positive or negative, all of these would come all the way around the outside, accumulate on the positive plate, and just sit there because they don't want to go back to the negative. That's unnatural for them to do that. Now, what a battery actually does in this circuit is, we're not going to get into the big part of why this is now. That's a future discussion. But really, we just want to say that batteries are adding energy into this circuit. Without it, the charges would sit there. But with it, and again, we talked about electric fields to this point, negative charges naturally want to go from negative to positive, which follows these black lines between these plates. However, the battery forces the negative charges to go from the positive to the negative so they get back on their natural path to flow. So what the battery's doing is basically just picking up these negative charges at this plate, dropping them over here so they can naturally flow back around the circuit, and this will continuously happen until that battery runs out and you need a new one to keep this circuit going. Looking at this same idea in a water pump analogy, I think sometimes helps. Really, if you look at this picture, what I've got going on is we've got, here's the ground, and vertically above the ground is going to be kind of like a water track. So if you were to pour a bucket of water here, it would naturally flow downwards, naturally down here, and naturally down to the bottom, and it would all accumulate here at the bottom. Well, let's say instead that you've got this water pump now that's connecting these two. So the natural water flow goes down this way, down here, and all the way to the bottom. The water pump takes the water down here and sends it upwards against where it naturally wants to go, back to this point, to allow this cycle to keep happening. Again, if the water pump wasn't there, all the water sits here. But with the water pump being there, it's able to continually allow this thing to move and to go. So kind of two different ways to look at it, but I think this helps a little bit in terms of giving you a visual for circuits, because it's obviously hard to see electrons traveling through wires. The other thing I want to highlight is how we look at resistors in both of these things. First, with the circuit, a resistor is just going to be this jagged line, just kind of like a wire that's bunched up, saying that it's harder for charges to get through that than it would for a straight line. Same idea here. It's easier for water to go through this pipe than it would be a pipe that is much narrower. So this is the resistance to water flow, whereas this is the resistance to charge flow. kind of similar in those things. What you're looking at back on the second page of your worksheet is going to be a couple of different setups with that same thing. So I'm going to give you the resistors and the circuit drawings, and next to them we're going to give you the water pumps and the water drawings. So what I'm asking you to do tonight is, can you, with the pictures I've showed you, with the mathematical work that you should now have, can you draw some conclusions for charges moving around wires using water and pipes as an analogy and a basis for that explanation? See what you can do. Answer questions 4 and 5 on the back part of this page. Bring that in tomorrow, and we will have a class discussion about that topic. Thanks for listening.